Hi everyone. So today we're going to talk about how big is aleph 2 and also aleph 3, aleph 4, aleph 5, blah 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 blah, all the way to aleph omega. And what about absolute infinity? Does it exist? So first of all, I have made a video about aleph-null and aleph 1 before, so maybe you can watch the videos first. So anyway, aleph-null is and all the aleph number here we're talking about are cardinal numbers, not to be confused with ordinals. Ordinal like omega, omega plus 1, epsilon naught, those are ordinals. They are for ordering, so first, second, third, fourth, etc. and etc. Cardinal are we talk about size of numbers such as million, Google, grams number, 33, those are cardinal numbers. And aleph-null, of course, is the smallest infinity. So this, kind of like a set of things. So it's the smallest transfinite number. You can kind of treat it that way. And some people call it countable or listable infinity. And aleph 1 is, of course, the second smallest infinity, and some people call that uncountable or unlistable infinity. And, obviously, as you see the pattern, so aleph 2 is the third smallest infinity, aleph 3 is the fourth smallest, so on and so forth. And again, I'm not going to talk about too much about aleph-null and aleph 1. Basically, aleph-null is basically the smallest kind of infinity, and also I think the easiest to understand. Examples include, the set of all natural numbers or integers, even, odds, prime. Those numbers, they have the same size, even though some of them, like the even number may seems to be smaller than the set of all integers, but however they are the same size because there's a bijection between them. You can pair them up 1 to 1. Let's say 1 to 2, 2 to 4, blah 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 blah. You can do that in forever. And then for aleph 1, of course, second smallest infinity, the difference is that you cannot list them. The first one, you can list them one by one. So whenever any set you can list them, they are the same size, is the smallest infinity. This one, the second one, aleph 1, you cannot list them. Is just, let's, for example, the decimal numbers, you cannot list them. So those are some of the examples of aleph 1. And actually, the size of the fast growing hierarchy, from F0, F1, F2, all the way to F omega, and then you continue F omega plus 1. And as you know, omega is the smallest transfinite ordinal. So even you continue all the way to omega to the omega, and then even omega to the omega to the omega to the omega, and epsilon naught, and even bigger and bigger ordinals, even all the levels in the fast growing hierarchy. Actually, it's actually the first smallest infinity out of no, because you can list them. That's that's the reason behind that. Why is it not? It seems to be, out of 1, because you can go past omega, omega plus 1, even some other bigger ordinals, but the problem is you can list them one by one. So there's a bijection, therefore it's the smallest infinity. So it's more difficult to list the examples of aleph 1, but of course, all the decimal numbers, so on and so forth. And even the set of real numbers, all the real numbers are said to be aleph 1 if we assume the continuum hypothesis is true. So the problem is, I do my research online, I couldn't seem to find any examples of aleph 2, because remember, aleph 1 and aleph-null, the difference between them is undescribable. Basically, you cannot reach aleph 1 from aleph-null. Same idea as you cannot reach infinity or aleph-null from the finites. It doesn't matter how many steps you do it, how many times you list all the finite numbers, you will never reach it, because that's the definition of infinity. You cannot reach it. Something not reachable, something goes on forever. If you can reach it, that means it's not forever, right? So the same idea, you cannot reach this from the previous level. So from doesn't matter how crazy you can think about things. Even like, let's say fast growing hierarchy, it doesn't reach this one, it's this one. And then even for this one, some people think about the points, because all the decimal numbers are points on a number line, so kind of think of it as a 2-dimension. How about number of points in 3-dimension, 4-dimension, even all the way to, let's say, Graham's number dimension, or even 3-dimension, even infinite number of dimensions? Those are actually still out of 1, or the total number of points, because they are all, you can treat that as, there's a bijection. So it doesn't matter how crazy you go, even the number of dimension will still be out of 1. So it's very difficult to find, an example of out of 2. Some people suggest, but it's just a general term, like the power set of the real numbers or something kind of complicated, but it's not an actual example. I guess you cannot find an actual example of it because this is infinitely bigger than this one. And that's a vast understatement, such as this one is infinitely bigger than this. It's vast understatement because infinity plus infinity is still infinity. That's why out of null plus out of null is still out of null. It's not out of 1. Even you plus, you add out of null together for an infinite number of times, it would still be out of null. Because countable plus countable, doesn't matter how many times you add it, is still countable. In order to reach uncountable, you need something that is uncountable. So, but again, actually, out of 2, out of 3, and so on, they're all uncountable. Basically, out of 1 and above is all uncountable, unlistable. But this is something more abstract. There's actually no example of that. This is unimaginably bigger than this one, and that's a vast understatement. Same thing for out of 3. Again, infinitely bigger than this, and that's a vast understatement as well. You cannot even begin to imagine the difference between those two. And so on and so forth. Each step is kind of unreachable from the previous step. And of course, there's no limit, just like the infinite number of finite numbers, or like there's no biggest number, you can always add 1 to it. So therefore, you can go all the way, all the finite numbers, let's say out of 3 something, and then even out of omega. And you don't have to stop there, you can go on out of omega plus 1, out of omega plus 2, out of epsilon naught, or even bigger and bigger ordinals. And remember, you have to put an ordinal number over here because that's for ranking. And of course, there's no limit of what's the biggest out of number. And you can just keep on forever. And therefore, as there's no such thing as absolute infinity. You can just keep going on forever and ever, just like there's no biggest number. You can keep adding 1 to it. Let's say it's kind of a paradox. There are a lot of paradox about infinity. Let's say you kind of assign a very, 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 very big ordinal nobody has ever defined before, but even that you can add 1 to it, plus 1, right? And therefore, this is just an idea or concept that some people bring it up. You can read the Wikipedia article. There's some kind of paradox to it. There's no absolute infinity. It's just something to think about, because there's no biggest thing, not even infinities. There's no biggest infinity. You can just going on and on and on forever. So there we have it. How big is out of 2? Is way, 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 way bigger than you think. I mean, out of no is already way, 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 way bigger than you think. Way bigger than 3 or anything, any finite number. So don't even bother to imagine it. So anyway, thanks for watching and have a nice day.